In the lab that we've done outside, we went out and tested for levels in the soil of things like nitrogen, phosphorus, potassium, and then we also tested the pH of the soil. Now, plants need these different types of nutrients and they need the pH to be in proper balance for their cellular physiology to function right. So you and I, as organisms, we have to keep our body temperature stable, right? We're warm-blooded mammals. We need to do that. The pH levels in our bloodstream and other places also needs to be stable because that's what helps regulate chemical reactions. We can die from a lack of balance in these types of things. And then we need certain nutrients for all kinds of reasons. You need really microscopic levels of iron to help circulate oxygen in your blood. You need extremely tiny quantities of iodine in your diet as well. And then we also need nitrogen, potassium, and phosphorus as well. So in plants, here we can see what some of the symptoms of a deficiency in these different things would be. But in this little discussion here, we're going to be going over exactly how plants obtain specifically these three types of nutrients, and then what the importance of pH balance in the soil is. And then we're going to talk about a few new groups of soils and exactly what makes them so good at growing crops. And then a couple of examples of soils that are really bad for growing things. So the first element is nitrogen that plants get in the form of compounds. So plants get the nitrogen they need primarily from ammonium and nitrates. Now, nitrogen is the most common gas in our atmosphere. 78% of the atmosphere is nitrogen. However, neither plants, nor bacteria, nor algae, nor you or I take in that atmospheric nitrogen and do anything with it. It's impossible. So we have to get it in different ways. Now, ammonium is a really stinky compound that's a product of decomposition. So natural compost that's made primarily from plant material itself, but a little bit from animal material as well, creates this ammonia as a byproduct of decomposition, and plants absorb and soak that stuff right up and put it into their tissues. We get our nitrogen from eating plants or other animals. Now, nitrates are produced by bacteria. They're the only organisms on the planet that can do this. And what they do is they absorb nitrogen from the air, which is pure nitrogen, and they combine that nitrogen with oxygen to form either nitrate, which is NO3, nitrogen and three oxygens, or nitrites, which is NO2, a nitrogen and two oxygens. Some plants have colonies of these bacteria on their roots. We call them nodules. And these groups of plants are called legumes. This includes peanuts and soybeans. The reason that we see crop rotation is soybean plants return nitrogen back into the soil. Corn does not, however. So you can't grow corn in the same place year after year, or eventually all the nitrogen in the soil will be soaked up. And the soil by appearance will look exactly the same. There won't be more or less of it, but what we can't detect is that it's nitrogen, or what we can't see rather with the naked eye, is that its nitrogen stores are depleted, and so you have to return that nitrogen back. The next one is phosphorus. So luckily, phosphorus is common within the regolith, which is the part of soil that's just made of broken down minerals. Phosphorus is in rocks. So there's plenty of phosphorus in the dirt itself. Now, phosphorus is different. Unlike other compounds like oxygen, water, carbon dioxide, nitrogen, phosphorus doesn't ever become atmospheric. It can't evaporate. It can't combine with other elements and become a gas. At least not on Earth it can't. What's the other thing that's essential though? Yes, there's plenty of phosphorus in the dirt, but there has to be water because water can dissolve rocks into really microscopic levels, and that's what allows the phosphorus to become absorbed. Or in other words, we say it becomes available. Available means it's in small enough quantities. Well, that's not how I want to say that. Available means that it's been dissolved to a small enough size that it can be absorbed. The reason you and I have a digestive system is because the food we eat needs to be broken down so that our individual cells, which are microscopic, can absorb the nutrient particles that there are. Can't do that with large chunks of food. So we need to chew our food and have acids and enzymes to really break it down. Now, pH is especially important for making available phosphorus. And we'll talk about why that is right now. If you look at the pH scale, if our soil becomes too acidic, below a pH of 6, what you can see in this graph is a huge percentage of the phosphorus starts to get fixated. And what that means is, because of the unique chemistry, the phosphorus atoms are forced to bond with other compounds, and then it becomes insoluble, which means it can't be dissolved by water. Well, again, water is the thing that breaks down the phosphorus to small enough levels where it can be absorbed. So we want to keep our pH in our soil not quite neutral, just a little tiny bit acidic, but not too much. Otherwise, bad things happen. This is part of why rainforest soils, as counterintuitive, are actually not very productive. There's huge amounts of rain and decay in rainforests, which makes very acidic water, which locks up a huge portion of the phosphorus that's available. And our final element here is potassium. Virtually all the potassium is in the regolith itself, so in the mineral makeup of the soil, but virtually all of it is insoluble, which makes it unavailable because it can't be dissolved in water. Dissolved potassium, it turns out, is found on the surfaces of clay particles, and that's what makes them readily exchangeable, or in other words, available. So again, water is a key component to breaking down minerals to where we can get them to the level where they can be absorbed. Now, this is what clay looks like under an electron microscope. Now, clay is just a dimension, a size of broken down mineral fragments. Sand grains are far bigger than clay grains. So sand grains are usually round in appearance because they've been mechanically broken down, and when that happens, things just tend to be, geometric in shape, roughly kind of roundish. But clay particles are so microscopic that they end up forming scales or flakes like this. And you can see just how they stack up on each other. Now, we can't see the individual phosphorus, but what you have to imagine here is on the edges, and there are lots of fringes and lots of surface areas here exposed, but only on the outer surfaces here is where the phosphorus can be directly absorbed and pulled out. If you can imagine the spaces between all these layers of clay particles, that's where the unavailable phosphorus is. And just by looking at this, we can tell that there's far more phosphorus that's inside of these layers and therefore unavailable than there is phosphorus that's on the outer layers and available. This graphic here is trying to show us this. Potassium is in the red, and we only consider the readily exchangeable ones to be, if you look in the circle here on the right side, the ones on the outer surfaces. Those can be directly pulled out. Ones in between clay particles, nope, you're not going to be able to pull those out. They're too hidden. All right, so a couple different groups of soil and why they're so good. Andizols. These are the soils formed by volcanic ash. So historically, people have lived around Pompeii, the volcanoes called Vesuvius. Why would we take that risk? Well, the soil is incredibly productive. The parent material, which is what the soil is made of, is tephra. Tephra is actually any group of rocks that are thrown from volcanoes. Now, what the heck makes volcanic rocks so fertile? Well, two reasons. The most important reason is that volcanic ash, because the ash itself is already really finely grained. It's microscopic for the most part because it's almost like dust coming out of the volcano. So as that ash piles up, it takes very little time for water to dissolve out the minerals and things in the volcanic ash to get to the point where plants would be able to absorb them. If you start out with bare rocks, it takes thousands upon thousands of years for mosses and plants and chemical weathering to erode it down to sediments that are small enough that can be absorbed. Volcanic ash, it's pretty much ready to go from the start. Another great thing about volcanic ash is because it comes out of the interior of our planet, it's very thoroughly mixed with a wide range of different types of materials. So it's almost like a multivitamin in that respect. So here's just some satellite imagery. That is Mount Vesuvius. So on the bottom portion, that's Naples. The city of Pompeii doesn't really exist anymore, but it sat pretty much towards the southeast of that volcano there. The last time it erupted was in the 70s. Luckily, it wasn't quite like the eruption in 79 AD. I think it was 79 AD. It was somewhere between 79 AD and 81 AD. I get that mixed up. This volcano is in New Zealand, a volcanic island nation. Now, if you notice the almost perfect green circle around it, the dark green on the inside is tree coverage. So that's a natural forest. That's why it looks so dark green. And we're looking at this image because, well, why is it so much lighter green around it? That's because all of those trees have been cut down. And we're talking about thousands of square miles here. So it's really incredible the rate at which people have been able to transform the landscape. This whole area, 200 years ago perhaps, was all a uniform, very dark green like we see there. So we're talking about literally hundreds of millions of trees likely that have been cut down just in this area here. And it's pretty hard to see. I'll show you. It's this brown dot right there. That is Mount Fuji volcano right next to Tokyo, Japan. So that's Tokyo right there. There are something like 45 million people in this picture. Here, this is the largest metropolitan area on the planet. And people have been living here for thousands of years because of what's available to them from the great soils. Now, obviously, Tokyo, it's not an agricultural society, obviously, but they got its start from, agriculture. Okay, the next group, prairie soils. So that's where we live, close to home. These are some of the most fertile soils in the world, but it's a bit strange. If the soils are so fertile, then why don't we see gigantic forests and things like that around here, like we do in the volcanic soils or in rainforests or things like that? Well, for a very particular reason. Now, the soil around here comes from glacial till. They melted around 15,000 years ago, but glaciers covered this entire area, and those glaciers started hundreds and thousands of miles north of here, and they dragged all kinds of material to where we are. And then that material has been broken down and eroded into the topsoil that we have today. Now, the reason it's not like a forest here, even though the soil is so productive it could support forests, is that it doesn't rain enough here. The eastern US, it rains far more than it does where we live here in the Midwest. And without copious amounts of rain, you cannot get forest coverage. If the climate changed and it started raining here much more frequently and we got much more precipitation, then we would see the eastern forests gradually migrate towards us. Although we would probably, in this age, be able to cut them down faster than they could advance on us. But that's the real reason why. Prairie soil ranges from 30 to 100 meters deep. That is extraordinarily deep for soils. Here we can see the middle of the United States. Let's get my cursor in here so we can actually see what's going on. These are the Black Hills. Those are the Badlands. So this would be Omaha, Nebraska right there. There's Chicago. Now this dark green here, this is all forest. And you can see how it gradually turns more and more brown, right? Because we're getting to more and more grasslands in this area. Now, we have totally terraformed all of this. If you pick any section within this Midwest region and you look at it, this looks all pixelated, but it's not really pixelated. It's just that we've ripped out all the ground of its native grasses and we've cultivated it now. We plant crops and things like that. So every square shape or rectangular shape you see here is a field that's been planted that way. And as far as unproductive soils go, we have loess. Loess is soils that pile up thick because the wind blows the material up into it. Now, these soils are, because they're formed from piles of wind blown sand, they have very little clay. And clay particles act as a bonding agent, remember. And so clay will lock together soil. Remember, bricks are made out of clay, so they do a great job of locking things together. But loess has very little of this. So some of the worst soil erosion in the world is from loess. And quite a lot of it happens in China. There's a great desert, the Mongolian desert, that brings lots of this wind-blown sediment. So you can see just how much stuff has eroded here. And then this picture, also in China somewhere. It will grow crops, but it erodes so quickly that it just is not stable. And then lastly, badlands. Now, we have badlands in South Dakota. We call them the badlands, but they really aren't the badlands. There are badlands everywhere. It's simply an area composed of soft sedimentary rock that is heavily eroded, but it doesn't produce regolith. Regolith means that the eroded sediments are very fine textured and able to form soils. The eroded sediments in badlands are large and coarse and chunky. Some badlands form in dry microclimates. The South Dakota badlands, for example, are surrounded by farmland and grassland. They just happen to be this one little area where it's much drier. And pedicle soils, which we learned about earlier, mimic, badlands, I should say, in a lot of ways mimic pedicle soils. So this is a badlands area. I don't remember the specific name, but in Utah. So really beautiful landscape, but you can see there isn't one single plant visible in here. Kind of way back in the middle, I see a tiny ribbon of green. But this is, you're not cultivating or even going to have any grass for animals to graze here. This is in Spain, so a little bit more green, but you can see very heavily eroded as well. This is Jackson Hole, Wyoming, another example of badlands. There are many places in South Dakota that look like this too. This is in, I think this is in Arizona. I can't remember the name. I know for a fact I have no pictures of the South Dakota badlands on here, just to illustrate the point that there are badlands in all kinds of places. And this is in Utah as well. More badlands. Not very much green. Lots of regolith, lots of eroded sediments, but it's not really soil the way we think of it. Thank you.